Hi, my name is Campolo, and today I'll be talking about my data science final project, modeling soils in sub-Saharan Africa. So the inspiration for this project is essentially that soil fertility management is essential to growing crops, and identifying soil properties is key to understanding soil fertility. So by modeling soil properties rather than manually measuring them, you can make agricultural predictions faster and cheaper. So the goals of this project are to obtain soil data and then develop three kinds of models: multiple linear regression models to predict important soil properties, logistic regression to classify soils as either loam or not loam, and finally KNN model to predict the soil horizon that a given sample belongs to. So first I'll go over the data acquisition and preparation. I got my data from a World Soil Information Database, which provides global soil parameter databases for download. Unfortunately, I had to download these files manually, but I did download three separate ones: one for Kenya, one for Central Africa, and one for South Africa. So I'll jump to my script now. So you can see that I downloaded these three separate databases into three data frames, and now I want to combine them. So in order to combine them, I had to do a variety of things. I had to make sure the columns were consistent and remove the ones that were not. I also attempted to impute some data, however the correlation for that missing data was very low. It was only 0.3, so I ended up removing that column instead. Finally, I ended up combining the three soil databases into one, which gave me one large database of 8,936 rows. At this point, there were still missing values. These missing values were coded as negative numbers, so for every negative number I replaced it with NA, and then I removed NA cases. So you can see now that, one second. So you can see here that after removing all the NA cases, there was 2.7% of the rows removed. But at this point, I have a clean database of 8,691 rows with no NA values. The second part of this analysis is data exploration. So first I looked at a paired panels graph. This will take a long time to run, so I'm going to skip it. But essentially, after that, I needed to determine outliers. Sorry, I'm just going to stop this. So here's just a subset of the panels, but you can't really see any of this, but there was, this is what I used to determine correlation and normality. So before jumping into that, I removed outliers. So after removing outliers, there was 12%. The database was shrunk by 12%. And then finally, I could look closer at the values that were maybe not normally distributed, so to see if I needed to transform them. So you can see in these graphs, a lot of these values were so not normal that even log or square root transforms didn't change them. But for some, like cation exchange capacity, log transform did improve normality. But the ones with highly skewed data, for instance base saturation here, they were unable to be transformed to get normality. So I transformed the ones that I could. You can see here total carbon with a log transform improved, and then also total nitrogen, a log transform improved the normality and made that change to my database. And finally, I looked at some values which, based on the paired panels, which based on the paired panels looked collinear. And indeed, there are some collinear aspects. So the percent clay and the percent silt is very strongly correlated with an R of 0.91, as well as pH and base saturation, and total nitrogen and total carbon. So this will come up later in my model selection and analysis. So finally, I created a loam column, which will be used for the logistic regression. So basically a soil can either be loam, which is good for agriculture, or not, and that's based on how much sand, silt, and clay is in the soil. In order to store this data in a database, I used a MySQL database. So I read my table into MySQL and withdrew a subset of that data, basically getting rid of the ID column, the classification column, and top depth and bottom depth, because they're both dependent on the layer column, which is what I'll actually be using. So for the linear regression, first I split into a training and test data set based on a random sample, and this just shows my backfitting. I'm not going to run through all of this because it took many steps, but at each step I limited the value with the highest P. So for instance, first it was this NA row because that was collinear as we examined before, and then the next one I think was percent clay, etc., etc. So finally, at the end, I had a model that was entirely significant with a R² of 0.44. Now that's a very low R², so this is not a very accurate model. And as you'll see in my analysis, so for a sample column, my prediction is 9.91, sorry, an example row, and the lower bound is 9.6 and the upper bound is 10.2. However, the actual value was 15 for total available water content. So the model's pretty off. The MAT is 2.37, which in context of percent, the model's averaging 39.24% mean average percent error, or mean absolute percent error. This can be seen in the graph of actual versus predicted versus a one-to-one line. The data distribution really doesn't follow the one-to-one line very well. So this is not the best model. I also built a multiple linear regression model for cation exchange capacity of soil. Again, more backfitting, removing the most significant, or the least significant factors until everything is significant. This model had an R² of 0.779, so it's better than the last one. Running my error analysis, with an actual value of 19, my model's predicting 28, so maybe for this example, still model's not doing too well. 0.7 is not the best R², but the percent error is much less, 13.5%, than the previous one. And you can see in this graph of actual versus predicted, it's very strong. It's tightly grouped around the one-to-one line. So at this point, this model had 10 parameters, which is a lot, and that's a lot to measure. So I decided to see if I could build a model with less parameters, only the ones which I knew from my classes were relevant to cation exchange capacity. So that was the percent of clay, the total carbon content, and the pH. So this model with a reduction of parameters down to 4 had an R-squared of 0.72, so only 0.05 less than the last model, and it's entirely significant, but it's based on a lot less parameters, so it's more usable. It requires less measurements in order to be effective. Once again, it's the visualization of this fit shows that it's still pretty tightly grouped around the one-to-one line. For the example I chose to make a prediction, I'm predicting 20.7 and the actual is 19.39, so that was a good prediction. Compared to the last model, the error has gone up a little bit from 13.5 to 15%. However, I think this is overall a better model because it relies on less parameters. So for the next part, I backfitted a logistic regression model, which is basically predicting whether or not a soil is loam. Scroll through my backfitting results here, and go straight to my error analysis. So comparing to the test data set, my model is getting 70% of the classifications correct. So this is not great and it's not super reliable, but it is better than a random guess, which would be 50% accurate. So one more model is my KNN model. I used a built-in library called class, and I used the KNN function from that. Now, in order to determine the best k value, I did a range of k values, basically from 1 to the number of columns minus 1 of the data set, and then found the optimal k within that. So here is a list of all the percent corrects for each k from 1 to the number of columns of my data, and the optimal k was 4, and the percent correct was 44.3% in classifying soil horizon. Now again, that's not a super high percentage, but if you were to randomly guess between 5 soil horizons, you only have a 20% chance of getting it right. So this does increase. This is better than guessing, essentially, even though it's not 100% accurate. So that's the conclusion. I demonstrated a variety of models and data cleaning in this project, and hopefully these models can give some insight into the agricultural world about modeling soil properties. Thank you.